All right, today we're going to be looking at the normal distributions. This is going to be kind of like a day one look at this type of uh, data distribution. It's called normal because it kind of happens so often. It occurs in a lot of things that have large populations or a large amount of stuff going on. We find that things are symmetric about what we call the mean, so that's center, the average. So there's some average number, and then things are normally distributed. So there's like a little bit bigger, a little bit smaller than what the average is, and then as you get more and more extreme towards the end, like extremely big or extremely small, there's less and less of those. And what we find is that a lot of like human characteristics and data follow a normal distribution. So, like heights, for example, there's an average height of men, an average height of women, let's say, and then as you get bigger and bigger and bigger, there's fewer and fewer of those people. So, for instance, there's very few people who are above, say, like 7 feet. There's very few people who are like below 5 feet, but there's maybe a lot more people who are somewhere in the middle there, like 6 feet. uh, IQ's kind of intelligence follows like a normal distribution where there's an average intelligence. Some people are very, very, very bright, but there is very, very few of those. Same thing on the other end. Um, and then this all, I mean, this applies to a whole slew of stuff. You'll find manufacturing processes. So if someone's producing a whole bunch of whatever it might be, the sort of like tolerance or error in between the manufacturing of all that stuff could follow a normal distribution. So some little sprockets might be slightly bigger, some sprockets might be slightly smaller, and then there's very few things that are really big or really small. And then you can also force things to become normal distributions. So, like, let's say I gave a test and the data was very, very low. You might want to see, like, on a test, you'd want to see, like, the average be a C average. However, you then want, some B's and some D's, not as many. And then you want fewer A's and fewer F's. You don't want everyone getting an A, you don't want everyone getting an F. So sometimes you can also force data. Once you kind of get your data, you can force it to follow a normal curve if that's what you want. Some key characteristics, though, are the normal distribution. It's symmetric. It's a bell shape, so it looks kind of like a bell, I guess, with its highest point over the mean or the average. So everything's kind of centered around this average. Um, when we say deviations, deviations means how far are you from the mean? How far are you from the center? So the bigger the deviation, the further away, whether it's a high deviation or a low deviation, or if you're deviating above the mean, so to the right of the graph, or you're deviating below the mean. The bigger the deviation, the farther away you are from the center. And so we kind of see like this example right here, this heights of adult US males. So we see 60 inches is 5 feet, so somewhere around there. 72 inches is 6 feet, kind of right there. So the average height of an adult male, whenever this was taken, is somewhere between 68 and 69 inches. So that's most people are around there. So somewhere between 5 and 6 feet. However, you can tell that then as the frequency, so how often does it happen? As you get bigger, there's fewer people who are 70 inches tall. There's fewer people who are 72 inches tall, so 6 feet or above. And then as you get bigger and bigger and bigger, that gets less and less happens. So you get fewer people who are 7 feet tall, which would be what, 7 times 12, that would be 84 inches. So you get fewer and fewer people who are 7 feet tall. In the same way, you get very few people who are smaller than 60 inches, let's say. All right, so moving on. And then what's kind of really cool, we'll see later, is that once you kind of have your data and it's a normal distribution, we have this rule called the 68, 95, 99.7 rule, which basically says that if you are within one deviation, so if you're kind of looking, let's say this thing, let's just say one deviation is from here to here, 68% of your data would fall in this range. The second thing is, well, two deviations. So let's say you calculate the standard deviation, which you've seen the calculation, how to do that in the prior lessons, but we'll use the calculator or Desmos to get that deviation. But you'll find out, like, okay, let's say my deviation is 2 or 3 or whatever it is. If I do one deviation, 68% of my data would fall within that range. If I do two deviations, 95% of all my data would fall within that. And that's a really powerful statement to basically be able to say, all right, if I know that the average intelligence or the average height of people is 68, 69 inches, and maybe the deviation's 1 inch or 2 inches, whatever it is, then I could say, all right, if I go a couple inches this way, a couple inches that way, I know that 68 or 95% of all the people, adult males, would then fall within that range of heights. And you can start using that to predict or to analyze data. All right, so we'll kind of look at these two examples in number one. It says compare the mean, so compare the center, and the standard deviation of these graphs. Again, deviation means how far is your data from the mean, from the center. Or the mean. Okay, so we look at these two graphs. We got this one right here and this one right here. And we can see they are symmetrical, and they're symmetrical about this number 10. So the mean, which we'll call x bar, is the same for both. So the mean is the same. They both have an average of 10. However, their deviations are different. So if I look at this one, I can see that most of the data, kind of right here, a big part of the data, most of that graph, kind of falls between 8 and 12. Most of that data is going to be between maybe 8 and 12, or even like 7 and 13. That's the vast majority of the data of your graph. Whereas if I look at this one, if I go from that same range of say 8 to 12, I really only have the peak right here. I really have to spread out, so I have to really spread out my data to get as far out as possible, to get all that data. So this graph here has a higher standard deviation, or what I'll just call S. Okay, its data deviates, has a higher deviation. So to get like the data, let's say the deviation is like 3 from your average, to get like 68% of your data, I might have to go to 13 inches and 7 inches or whatever it might be. To get 95% of my data, I might have to go another 3 and get like say 16 and then 7 and 4 to get most of my data included in there. Whereas with this graph, the one that has kind of like that tighter shape, I only have to, or higher peak right here, I only have to go a couple spaces over to get most of my data. In this graph right here, their means are different. The average for this one is 6. The average for this one is 14. But we can see that their deviations are the same. So if I want this much data, just circling it, I only have to go, say, 3 spaces that way, 3 spaces that way. The same thing here, that same amount of that graph, the amount of data there, is I only have to go the same amount left and right. So this one, the means are different, the average is different. But the standard deviation, the S, is the same. All right. Which distribution appears to be normally distributed? Well, this thing is kind of clearly skewed to this lower region right here. It does not follow a normal kind of looking distribution. It's not symmetric about a mean. Whereas this one kind of follows the shape of the bell, where you get most of your data clustered around the center, this mean. It's symmetrical about this mean, and your fewer and fewer results at the extremes. So this one would be, appears to be normally distributed. Moving on. Which of the following would you expect to have a normal or nearly normal distribution? The age of a person on vacation in Las Vegas, or the shoe size of an adult woman. Again, a lot of human characteristics are going to have a normal distribution. So the shoe size, there's going to be an average shoe size for women. Stores would stock this more often, and then if you have a really big shoe size, it's harder to find those shoes. There's only so many of them. The same thing on the other end. So the shoe size of an adult woman would probably be normally distributed or nearly normally distributed. The age of a person on vacation in Las Vegas, if you think about who can travel to Las Vegas, who would enjoy Las Vegas, this would probably be skewed to people who are older than 21. I forget what the gambling age is. I think the gambling age is maybe 18, but the drinking age is 21. So, and having money to even do that stuff, probably older than 21. So you're not going to get that nice neat distribution. And then you probably have, I would imagine, a lot of old people too who go there for retirement, and then a lot of young people who are going there for fun and parties and whatever else have you. All right. Number 4, female adult heights in North America are approximately normally distributed. So this is important. They told you it's normally distributed with a mean, so an average of 65 inches, and a standard deviation of 3.5 inches. Find a height that's 3 standard deviations above the mean, 2 below the mean, 2.5 deviations above the mean. So again, what's happening and what we'll be able to see, what we're going to be using is actually this rule a little bit later. But you can imagine if it says it's normally distributed, you can automatically think that you have this bell-shaped curve. And in the center is going to be the mean of 65 inches. So that means some people's height are going to be a little bit bigger, some people are going to be lower. And they calculated, so they had all this data of heights, and they did the calculation for normal distribution, for standard deviation, and found that it was 3.5 inches. So 3 standard deviations above the mean. If I go 1 deviation above, that would be, I'm just going to kind of mark it here, that would be 68.5 inches. That's 1 deviation above the mean, bigger than the mean. If I went 2 deviations above, that would be another 3.5 inches. So 3.5 inches there, that was 68.5. Another 3.5 inches, that would be, 71, 72 inches. And then that third deviation, one more deviation of 3.5 inches. So 3.5 for the first one, 3.5 for the second one, another 3.5. That would put you at 75.5 inches. So find the height that is 3 standard deviations above the mean. That would be 75.5 inches. Now the shortcut for that is to say, all right, you're starting at the mean, 65 inches, and because you're going above, you're adding to that 3 deviations, and each deviation was valued at 3.5. So 65 plus 3 times 3.5, you're going to end up with 75.5. Okay, 2 standard deviations below the mean. So this time I'm going below, so to the left, and I'm going 2 deviations below this thing. So if I subtract now 3.5 inches, that would be 1 deviation below. So that would put me at 61.5, I believe. Yep, 61.5 inches. And then if I, again, subtracted 3.5, that would put me at 58 inches. Yep. So 58 inches is the height. That's 2 deviations below the mean. And again, because I'm below the mean, I'm going to start at my center. But because I'm below, I'm going to subtract, go to the left, 2 deviations, each deviation valued at 3.5, which would put me at 58 if my math was right. And then 2.5 standard deviations above the mean. So this is 65 inches. That's where your starting point is, the mean, and then you're going 2.5 deviations above that. So because it's above, you're adding, you're going to the right, and you're doing 2.5 deviations, and each deviation is valued at 3.5. So pull out the calculator. 2.5 times 3.5 gets you that, plus 65. That puts you at 73.75 inches. Okay, so this is how you go from the mean. Once you know the mean and you know the standard deviation, you can start saying, all right, here's this data that's 1 deviation from the mean, here's the data that's 2 deviations, and so on. So with that being said, we have this very special rule that we're going to be basically using the rest of the time. It's called the 68, 95, 99.7 rule for the normal distribution. It's literally like the coolest thing ever. So, it says approximately, again, approximately, not 100% exactly, but pretty darn close, 68% of your data will fall within 1 deviation of the mean in both directions. So if you go 1 up and 1 deviation below from whatever your average is, your mean, 68% of all your data will fall in that range. If you go 2 deviations, 95% of your data is going to be there. So that's like the vast majority of everything. You could basically be pretty certain of saying, all right, only 5% of the people are going to fall above those extremes, those 2 deviations, and you can use that data. And if you want to be super exact, you can say that 99.7% of your data is going to be within 3 deviations. Now, this is not 100% of your data, so there's still 0.3% left over. So what if you go 3 deviations one way and the other, there's still 0.3%. That means that there's still 0.15% above 3 deviations and 0.15% below 3 deviations. So that's where your 100% comes from. So 15 and 15 gets you 0.3. There's 100% of your data. Okay, but within 3 deviations, 99.7% of your data falls within that range. So let's see some use of that. All right. So use the distribution of male adult heights in the figure above to find the percentage of men with heights within this range. I'm going to make this a little bit smaller. Too small. First lecture on